So, hello everyone, I'm Aurelien Piluso and I'm here to talk about my results about the estimation of the physical conditions in PDRs from IGRIN's raw vibrational H2 observations. So, first of all, we're investigating the poorly understood problem of stellar formation, particularly at really small scales. The interstellar medium there acts as a reservoir of molecular gas for stellar formation. Indeed, a portion of the clouds at a moment of time undergoes gravitational collapse, leading to the birth of a star. Then, this newly born star exerts feedback on its parent cloud, either mechanically or radiatively. In our case, we are going to focus on the radiative part. If we zoom into this region, the radiation coming from the newly born star creates a photodissociation region, or a PDR, which has been perfectly described by Emmerich just an hour ago. So this is by definition the interface between the H2 region and the molecular clouds, and this is where we find warm and dense gas, which emits in infrared and millimetric. This is those excited molecules, which could be the tracer of this radiative feedback. And you really need to understand that the physics of PDR is fundamental and at every scale, going from the protoplanetary disks where the GWST is revolutionizing our view, to the diffuse interstellar clouds and all the way up to stellar forming galaxies. PDRs play a major role on everything, acting all the way from the infrared emission spectrum of galaxies to the conditions for planet formations. So you know everything already on the PDRs, but a quick reminder. So close to the massive stars, the UV illumination is going to ionize all the species, creating the Strom-Grain sphere. And then from the ionization front over there, only far UV photons penetrate deeper into the PDR, only dissociating the molecules. Therefore, the PDR is a gradient of ionized atomic and molecular species, and is by definition the place where the radiative feedback acts on the molecular cloud. And this part is really important because this feedback impacts drastically the physical conditions of the clouds. It could be the pressure, the temperature, the density, the chemistry, and all of those conditions are really key to stellar formation deeper in the cloud. So here, my main goal is to answer the question of what is the impact of a radiative feedback. Ooh, really quick. Ooh, how did I do that? I have no idea. Maybe if I... Okay, even weirder, sorry. I'm there and present. It's even loading now. Okay, so it will come at some point. Yeah, so because this impact is really difficult to understand, because on the one side, it favors the stellar formation by creating overpressured region, but on the other side, it prevents stellar forming regions by dissociating H2 and spreading molecules all around. So my aim here is to determine and constrain the physical conditions which could be issued from the UV illumination. In my case, I'm going to constrain the thermal pressure and the UV illumination particularly. To do so, we can use different tracer, and in my case, I'm going to use the H2 molecules, as it is the most abundant molecules in the interstellar medium and acts on a lot of physical-chemical processes occurring in PDRs, but also because we have like a huge, great amount of detections of H2 raw vibrational lines coming from different instruments currently. So just to really understand where those raw vibrational emission detections come from, here is a potential energy diagram of H2. And the ground state H2 molecules populated by thermalization are pumped all the way up to the Lyman and Werner bands thanks to the UV illumination of the stars. Then most of the excited molecules undergo fluorescence and go back to the ground state, but at high excited raw vibrational levels. And then those molecules undergo raw vibrational cascades and emit in the infrared. And this is the part that we can observe with different instruments here. So to do so, we can use different instruments, as I said. So either space-based telescope like GWST NIRSPECT or ground-based spectroscope like IGRINS, which is the case of my work here. So IGRINS is a spectroscope covering only the H and K bands, so really narrow bandwidth, but has a really great spectral resolution of 45,000, allowing us to detect more than 100 of H2 emission lines. So we are using observation made in 2021 by Kyle Kaplan of 5 different PDRs, which can be split into 2 different groups. So 4 of them are moderately illuminated PDRs with the Horsehead Nebula beautifully presented by Leontine this morning, but you all know now. And there is NGC 2023, Sharpless 140, and IC63. And then we have also in the sample 1 intensely illuminated PDR, which is the Aurelien bar. Sadly, we lose the spatial information as we average the intensity on a slit, which is the really small green rectangle there. So to answer the question of Frédéric on beetroots, when we're going to sample everything, it's going to be on 1 pixel in the end. So yeah. So some primary studies have been performed on those observations, but since we have calibrated the data, so that means that we now have the absolute intensity, we have also improved the extinction correction of the lines. And most of all, we are going to use the Meudon PDR code, which is a code that you know perfectly well now, using detailed physics to understand really the extent of the observation that we have. Before going to the modeling part, I really want to highlight how unprecedented those observations are by highlighting this excitation diagram of the Aurelien bar. So here on the x-axis, you have the different levels of the detections of H2, separated on the different vibrational levels. And on the y-axis, you have a value proportional to the column density. So to compare this detection with the previous detection made by other instruments, we can see that, for example, PDR detections only were able to detect around 10 pure rotational H2 lines, and even NIRSPEC is able to detect around 30 to 40 H2 lines and going only from V equals 0 to V equals 5 to 6. Here we have more than 100 H2 detections, and going from V equal 1 to V equal 12 and even V equal 13. So that's really a huge data set that we have, a really interesting one. And the goal here is to use the best tool possible to extract as much information as we can of those kind of observation. So to do so, I'm going to use, if that works, yeah, if that works, the Meudon PDR code that you know properly now. Which is a state-of-the-art code using the assumption of a 1D stationary either isobaric or isochoric model to put more details about the physical processes really occurring into the PDRs, like the radiative transfer, taking into account everything from the UV to the radio domain, with the absorption, diffusion, scattering, continuum, and lines in general. We have also like a really great chemistry network considering more than 100 species linked together by thousands of chemical reactions, either on gaseous phase or at the surface of grains. And for the most important species like H2, COOH, HCN, we even compute the quantum levels of those species, considering every processes populating the levels with collisions, radiation, chemistry, and so on and so on. And as everything is out of thermal equilibrium, as Emric said before, we need to take into account all the thermal processes here with all the heating and cooling processes. And all of this is solved together iteratively at every depth in the cloud until the code converges. So in this way, we are able to model really in detail one PDR. But here, what we want to do is to estimate and constrain physical parameters. So what we're going to do is create different grids varying parameters. So here, I'm going to use the 2 main parameters for PDRs, which is the thermal pressure and the UV field intensity that we're going to normalize and call G node up to now here. So we have a grid of around 200 models there. And to quantify the relevance of those models compared to the observation, we're going to use both approaches, so a classical chi-square minimization and a more advanced Bayesian inversion and posterior exploration, thanks to beetroots, Pierre Talus working here, and you have everything you need to know on beetroots now. And if we want to go even further in this grid and to refine it, not to have like a discrete grid, but to get to a continuous grid, we can even interpolate within the model grid using either a nonlinear interpolation or neural networks with NMDMA, which has been presented again just before. So here I'm in a way a great practical experience of all the methods and models explained and detailed before. And I'm putting everything into a physical context to really constrain physical parameters here. Yeah, so the results, so I computed one grid for each PDR and the observation, and we tried to compare all of them. And the results split it all again into two parts, with the results for the moderate PDR on the one side and the results for the intense PDR on the other side. So here I'm going to present the results for the Horsehead Nebula case here, but keep in mind that those results are really similar for all of the other moderate PDR stated here. So here we have the excitation diagram for the Horsehead Nebula. And now we can compare this by exploring the parameter space here into 2D here with the G node and the thermal pressure, and to have a contour of chi-square minimization. So first of all, what we can see here is that only a few parts of this parameter space can explain properly the observations detected there. So that means that the H2 emission lines are really sensitive to both thermal pressure and the G node, and we're able to constrain really properly those physical parameters using only H2 as a tracer. We still have some degeneracies with this significant L shape here, but we're going to lift it right after that. We can now plot the best fitting model here, which is the minimal chi-square in red point here. And we see that more than 90% of the lines are reproduced within a factor of 2. So that means that the Meudon PDR code takes into account all the physical processes necessary to model properly the physics of the PDR actually happening there. But as I said, we still have some degeneracies, so we want to lift this. So I had to add some specific constraints for every PDR. So here in the case of the Horsehead Nebula, I had to add a condition on the distance between the ionization front and the transition HH2, which has been observed. So we have at least a maximal value here. And we can refuse all this shaded region here because it didn't fit this observation here. And so we end up with only this part, which is able to reproduce properly the observation. And the green model, which is the new best model with the constraint here, is still reproducing more than 85% of the observation within a factor of 2. So that's still pretty great. And with the help of beetroots and the Monte Carlo Markov chain exploration, we can even explore properly the parameter space and sample and quantify the uncertainties behind this, which is the first time that we are able to do that on those parameters there. So this is the case for the Horsehead Nebula. It's globally the same thing for the other moderate PDRs. And for the Aurelien bar, it's somewhat a little bit different here. As we can see, the contour plot is much wider and flatter. So that means that the H2 emission lines are less sensitive to the parameters than for the moderate PDRs. And we need to add again some other constraints here to constrain properly. So we know for a fact, for example, for the Aurelien bar, that we have at least a G node of 10 to the 4, thanks to the minimal distance between the star and the ionization front. But we still see that we have some degeneracy there, and we can't constrain this even more. So we need to add some other tracers in this case, and this is my current work, by adding another species with the CO observation, and more specifically, the raw vibrational H2 CO emissions, which is the first time that we're able to observe CO raw vibrational emissions in PDR. And I'm trying to sample this currently and to add those to the H2 observation to see if we can really fit all of those models and lift this degeneracy here. We still see that the two best fitting models, so the red one here, which is not physically acceptable there, but even the green one, are still fitting more than 85% of the lines within a factor of 2. So that's still really pretty decent here. All of this modeling is enabled thanks to the really detailed physics happening into the PDR. And we can see that with those two different figures here, where we have the different contributions and of the processes populating the different levels of H2. And we see that we again have a difference between the moderate PDR and the intense PDR, with the moderate PDR being populated mainly by the downward infrared cascade, as I told you about before, compared to the Aurelien bar, where most of the levels are populated mainly by the downward collisional transitions. So these figures illustrates really that we need to take into account in detail the collisional transition and the collisional rates, even at high energy level, to model properly the physics happening in PDRs. Another thing that we can do, thanks to this great amount of lines detected and this thorough exploration of the parameter space in general, is to constrain the microphysical processes also occurring into the PDRs. And here is an example with, for the first time, the possibility of constrain the distribution at formation of H2 occurring mainly in the moderate PDRs. So here, we compare two different distribution at formation of H2. So one is a classical thermal Boltzmann distribution here at low vibrational level and spread into the different J level, compared to a distribution suggested by Cizin in 2010 using potential energy surfaces calculation. Suggesting a much different distribution there with a greater vibrational level distribution and a lower rotational level distribution here. And we observe for the first time a difference in modeling in these PDRs, mainly for the moderate PDRs at V equal 1 at high J. We see here a good improvement of the modeling thanks to the Cizin prescription. So that means that we can now constrain, and we know that for a fact that H2 forms preferably vibrating more than rotating, mainly in the moderate PDRs. So this is my last slide with the three take-home messages, which are: first, it is essential to include complex chemistry and numerous microphysical processes to really realistically reproduce the new observation, even with that huge amount of detections. That the H2 raw vibrational lines allow for a detailed study of the physics and the microphysical parameters in general, but it's not enough. We really need to add some specific constraints, either observational constraints or even add over tracers for the case of Aurelien bar. And the advanced numerical techniques like the neural network and the Bayesian inversion that I presented a little bit here unlock really the full potential of the complex data sets on the one side and the complex models used on the other side, enabling rigorous parameter exploration and unprecedented uncertainty quantification. So that's all for me. Thank you.
Thank you, Aurelien. So is there any questions? Yes.
So if you go to your models where you have these ortho and para measurements, so Orion B seems to have.
Yeah, great. I know where you're going, but yeah. I'm sorry, it's lagging.
So here, for instance, in this the Horsehead Nebula, if you see at the ortho and para, they have different column densities, while in Orion B they have similar, or apparently similar column densities, although the model still goes up and down, which I guess is the different ortho and para transitions. So my question is whether you are considering that or you can model the ortho para ratio because it seems to change already in the data. So
yes, totally. So we compute the ortho para ratio. We compute really every state of H2 separately with everything happening there. So every level populated with the exact prescription. But we see here that we still have some discrepancies mainly visible in the Aurelien bar, where we systematically overestimate the para levels. And that's an issue that I have highlighted in my paper that I'm currently submitting. I don't have the explanations there, sadly. But yeah, so this is something that we're still trying to work on. So all the ortho to para ratio are logical with all the qualitative and all the calculation, the theoretical calculations about this, mainly in the moderate PDRs, but for the intense PDR, we still have some discrepancies on the ortho para ratio. And we're still working on this. But yeah, this is
And very briefly, so does it change, or is just the observation that looks like that? So is it the true orthopara ratio changes from region to region?
Oh, yeah.
Oh,
For moderately illuminated PDRs are having a much lower orthotopa ratio compared to the Aurelien bar.
Okay.
But our modeling are not perfectly aligned with the observation yet.
Well, very interesting. Yeah. Thank you.
Thank you.